we're at 23.4. I'm pretty sure. Now this should be 22 point, right? Okay, we're at 23.45 right now. That's not bad. If we were tilted to the maximum degree, that would mean that in the winter, in the summer we get the maximum amount of heat, and in the winter we get the maximum amount of cold. If we were tilted to the smallest amount, then the summers would be mild and the winters would be mild. So if you're in this extreme, it's hot in the summer and cold in the winter, and if you're in this one, it's more equitable. So what brings on ice ages is when three things coincide. This, which is axial tilt, but I love the real name of it, it's called the obliquity of the ecliptic. Isn't that great? The obliquity of the ecliptic. And all that means is that we're tilted more sometimes than the other. And if you're tilted a lot, you've got more chance of going into an ice age because you got hotter summers, but get this, colder periods. Now wait a minute, that's what people used to think. Then a guy named Milutin Milankovic, I don't think I'll write that all over the board. He's a Serbian, it's not his fault. Anyway, Milutin Milankovic came up with the idea of what are now known as Milankovitch cycles. And in a nutshell, it says the Earth's orbit around the sun varies in its ellipticity. Sometimes it's more circular, sometimes it's more elliptic. That varies over a period of about 100,000 years. So when do we get the most heat? Well, whenever we're closest to the sun. So sometimes it's round, sometimes it's more of an ellipse. If it's more of an ellipse, you're going to get more variation in the seasons, right? Okay, that's one thing. So we got the obliquity of the ecliptic, which is the tilt. We've got the orbit around the sun. Right now we're orbiting at 107,000 kilometers around the sun. That's the speed. And by the way, I told you this, I think, that I look down at the Earth under my feet and I realize, because I'm standing on the 50th parallel, that I'm doing 1,073.3 kilometers an hour. Because that's how fast the 50th parallel is going. But if you move up to the North Pole, what are you doing? If you're standing on the North Pole, you're not moving at all, right? That's a day.
Yeah.
On the North Pole. But if you're on the equator, where you're doing 1,075 kilometers an hour, you're really whipping it around, right? You see why the ancient Greeks didn't want to believe that the Earth was spinning on its axis, or why it was going around the sun.
let's make a planet, shall we?
Sorry?
So shall we make a planet?
A planet.
Yeah. We had a molecular
Oh, well, anyway,
cloud.
let's carry on with the molecular cloud. I
That's right.
apologize for that deviation. So, the molecular cloud gets shocked by a supernova. It turns into a
nebula?
protoplanetary disk, which becomes a nebula. What is happening is that gravity, when the supernova goes off, it shocks the molecular cloud. That shock causes gravity to make the thing start contracting. As it contracts, angular momentum starts spinning. It starts spinning faster, and it spins faster and faster, and the stuff clumps more and more toward the center, until finally, all the small parts either destroy each other that are going around, or they hit each other and destroy each other, or they hit each other and accrete. So things are getting bigger as they go around the sun, and they're gradually clearing out paths by smashing other things out of the way. And so we have areas where the planets are going to be forming. At about 100,000 years, we get a proto-sun. Now that is not a real honest-to-God sun. That's just the sun getting hot. It's not got nuclear yet. It's just getting hot. So it's still chemical reactions, not nuclear ones. Sun gets hotter, and at a certain point, well, exactly 3 million years after that starts to form, so 4.97 billion years ago, the sun fires, the first planet forms, and that's Jupiter. Let's look at Jupiter. Well, we're not looking at it, but that's nuclear fusion. That's what's going on in the sun right now. Okay, there's the solar system. I'm not really crazy about that. We couldn't get a good one. I may have to draw it for you. But anyway, Jupiter formed first, I mean. So, here's the sun. Okay, there's going to be the 4 Rockies, and then we're going to have the 4 ice and gas giants out here. And the furthest one out is Neptune, and then we're going to have Uranus, and then we're going to have Saturn, and then we're going to have Jupiter. It's the first one to form. It got all the stuff. That's why it's the biggest. It was the first, and it got the most. Jupiter formed first, followed by Saturn. So you got Jupiter, bigger pardon. Sorry. Never done this before. Okay, so there's the those are 2 ice giants. Here's the 2 gas giants. This is Saturn, it's got a ring around it. That's Jupiter. Then you're going to have the 4 rocky planets in here, and that's us right here. Okay, so first planet to form is Jupiter. Jupiter is monstrous. It forms, followed shortly after by Saturn, and then at some other time by the next 2, which are Uranus and here's Neptune, right? They're in order, but it's just harder to see, right? So we got the ice giants out here: Neptune, Uranus, Saturn, Jupiter. Then the inner rocky planets, Mars, Earth, Venus, and Mercury. That's the sun. And there's a bunch of asteroids in here. Yep, asteroids. And then there's a scattered disk out here and a Kuiper belt, and way out halfway to the nearest star, there's the Oort cloud. And that's the solar system. So, solar system forms Jupiter first, then Saturn. Then what do? They get into a resonance. That means that for every 3 times Jupiter goes around, Saturn goes around once. And they end up, so Jupiter goes around twice to Saturn's, or 3 times to Saturn's 2 times. These 2 planets, the 2 big boys here. And for reasons we have to go into, they decide they're going to migrate. So Jupiter migrates, takes Saturn with it. This is the asteroid belt. It's full of rocks of various sizes, everything from the size of planets down to meteors. Anyway, they plow through it, and they cause the asteroid belt to scatter in all directions. So Jupiter and Saturn migrate through the asteroid belt. Then they turn around and migrate back out. And they end up further out here than they started with, closer to where they are now. And so we got the gas giants. They're mainly water, ammonia, a bit of methane. Same with these ones, except these ones are a lot colder. So we got the gas giants and the ice giants. And then Jupiter goes on its migration, wrecks the asteroid belt, moves back out. Then the sun fires up. So sun finally goes nuclear. Starts fusing hydrogen into helium. And for the last 4.55 billion years, the sun has been fusing 600 tons of hydrogen into 594.5 tons of helium every second. And it's still doing that. And it's still there. That's the amazing part of it. It's still there after. It shows how big it is, right? It's been doing that for the entire life of the solar system, and it's not that much smaller than it was originally. It's not going to disappear. We don't have to worry about it. We'll lose the moon eventually because it's moving away further all the time. It's the old fingernail thing again, about 3.78 centimeters a year. But the sun isn't, so we're going to keep the sun. The rocky planets form. Now the formation of the Earth. And I can't talk about the formation of the Earth without talking about the formation of the moon. Now I'm not going to panic. Last time I kind of saw that I was running out of time and became even more incoherent than I usually am. So this time I'm going to try. I mean, I can hear Time's Winged Chariot, right? But that's all right. Just back off, Chariot. I don't care. All right? So this is fusion. That's what the sun's been doing. There you have your proton being turned into a neutron by colliding with another proton. One turns into a neutron. There's another collision. You get deuterium, which is an isotope. It's a nibble with a proton and a neutron. Then when those collide together, you get a helium. Now the difference is that hydrogen's got 1 proton. Doesn't matter how many neutrons it's got. Forget it. It's the protons that count. If it's got one proton, it's hydrogen. If it's got two protons, it's helium. If it's got three, it's lithium. If it's got four, beryllium. If it's got five, it's boron, so on and so on, right up the line. So that's what counts. So what happens is a proton becomes a neutron becomes deuterium becomes helium, a helium-3 nucleus, which gets bombarded again, becomes a helium-4 nucleus, and that's the fusion that is occurring in the sun. And we're trying to do that on Earth, but they're not trying to do the same process. I don't know, I can't remember why, but it wouldn't work. So the fusion that they're trying on Earth is not the same as the fusion in the sun. That's called proton-proton fusion. Whatever they're going to try to come up with on Earth, they need it way hotter. In the sun, it's only 15 million degrees, but on Earth, the temperatures we're looking at are 100 million. So that's where the problem comes in. I can't see it happening anytime soon, but I don't know for sure. Like I said, my grandfather was born in 1885 and died the year they put a guy on the moon. So he was born in the same year that Daimler invented the internal combustion engine, 1885. And he died in November, I think it was 68, and I remember 1969, I'm walking down Granville Street. I'm on the left-hand side of the street, on the right-hand side of the sidewalk. The sun's out, shining on me, just like it should be. And I heard that they put a man on, well, it's a spotlight, right? Anyway, they put a man on the moon between July 16th and July 24th. I remember it well. I'm not sure why. Oh yeah, I'm talking about it because I'm trying to illustrate the scientific progress and the change that has occurred in the lifetime, the relatively brief lifetime, 83 and something years of one person. And in our lifetimes, things have changed even bigger. When I graduated in 1960, Watson and Crick had only come up with a DNA thesis 7 years before. It wasn't even in the textbook. So that's my excuse. If I don't know anything about genetics, it's because it wasn't invented. They still let us doing Punnett squares. But I assume that they're teaching more modern stuff in science now. So I'm just blown away by the amount of things have changed. By the way, the moon. Got to tell you about the moon. Okay, so about between 4.54 and 4.43, but most likely about 4.451 billion years ago, a Mars-sized object came along and smashed into Earth. There were various theories about how the moon formed. One I like was brought up in 1877 by Charles Darwin's son, George, and he said that the moon was created when the Earth was spinning really fast and part of it flew off. And it took a long time before they finally found that wasn't true. And then it wasn't ever spinning fast enough for that to happen. And then another theory was that, well, something came by and Earth captured it. You know, the moon was making its way through the solar system and it got into Earth's gravity and next thing you know, it's doing revolutions, right? That was a popular theory too. The other one was the accretionary hypothesis where the moon formed at the same time as the Earth, right? The Earth was formed out of smaller chunks. They all got together, got really hot, then they cooled down, that was the Earth, and the moon formed the same way. Well, no problem, until they got to the moon back in 1969. And let's take a look at the, let's see, probably look at the two sides of it. Or, no, let's carry on with the, probably can look at the two sides of it, and then we'll look at the impact. Just show me the next slide, baby. Okay, there's the two sides of the moon. You can see that the far side and the near side are pretty different, right? The far side, as you can see, has only one dark spot in it. That dark spot is 1% of it, and that's part of what you see in the middle. That's the second biggest impact crater in the entire known in the universe. And this impact crater, which is near the South Pole, so called the South Pole Aitken Basin, it was created at, let me think, about 4.33 billion years ago by an impactor that created a 2,500 kilometer diameter crater. So that impactor, they figure, was about 170 kilometers across. Now, if that doesn't mean anything, I just want to address you to the dinosaurs. This is when they died out, right here. And an impactor came down and creamed the Earth right off the Yucatan Peninsula, you know exactly where it happened. And that bolide, or that asteroid, or whatever it is that hit the Earth, was 10 to 15 kilometers in diameter. 10 to 15. That was 170. So when they got to the moon, and they saw all those craters, there's 330,000 craters there that are more than 100, that are more than a kilometer across. When they got to the moon and saw how badly it had been pasted, they thought, well, that's it. There could not, like whatever happened on the moon happened on Earth, right? So whatever happened on the moon happened everywhere in the solar system. So they said, okay, there was this thing called the late heavy bombardment, which says that between 4.1 and 3.8 billion years ago, all these asteroids were coming down and hitting everything, and that meant that the Earth at that time would have been uninhabitable. It would have been impossible for any life to be there, because you had constant rain of asteroids coming down from outer space. Some of them great big huge things, like the one that created that basin. And everybody said, well, obviously life could not have existed on Earth from the time it was created for the next few billion years, or for the next billion, or at least 500,000 years. It would have been too hellish. That's why this first era here is called the Hadean. Now Denise said, could I write it off, rub it off, and I said no. Now, I was waving a book around last week that is in the library here that I was telling you was a really good book, and it was written in 2011. All the latest stuff, and it does not have the Hadean era in it. That is because that recently they did not have enough information even then. So if the book was put out in 2011, most of the information is the kind of stuff that was around 2000, you know, maybe 2005, right, something like that. At that time, there was not enough information to even declare that there was a period called the Hadean. It is now an internationally, officially recognized first time period for the Earth, and it means hellish. It's named after the Greek god of the underworld, Hades. So that's the first period. So that's this period of the Earth's history. And people said, because of a late heavy bombardment, the evidence of which was there on the moon, because of a late heavy bombardment, life on Earth would have been impossible at an early date. Earth would have been molten. That's the moon right there. Okay, let's do the moon, because you can't do the Earth without the moon, because it was so cataclysmic. So 4.53 or 4.51 billion years ago, there's the Earth cruising along. Something the size of Mars comes along and smashes into it. That body is called Theia. That's the name they gave it to it. It has to do with the Titans in Greek mythology. Theia comes along. Theia's about as big as Mars. Okay, Mars is half the size of Earth in diameter, but Earth is 6.6 times as big in terms of volume. So a considerably smaller, but nonetheless still big object comes along and smashes into it. And these computer simulations here, by the way, which are pretty recent and extremely huge, they had tremendous computing power in this. They ran all this stuff through, and this is what they came out with. So Theia hits Earth. A lot of Theia gets vaporized, and the rest gets melted. Some gets destroyed altogether, right? So Theia hits the Earth and really suffers. Earth is melted and the outer part vaporized, but nobody's sure how much. So most authorities think somewhere between 1 2/3 or 3/4 of the Earth was either melted or vaporized, and nearly all of Theia. And huge temperatures result. Theia, a mixture of Earth and Theia, starts revolving around the Earth at the Roche limit. This gives me a chance to tell you what the Roche limit is. Once again, to be so happy I'm up here holding forth and listening to myself talk, which is that's not the only reason I decided to give this. It wasn't just what I said last week when I was talking about Mark Twain and the 2 reasons, but I honest to God, it was a challenge, and I wanted to see if I could do it. I have to admit that. Okay, I'm using you guys as, could I actually take something as big as the history of life, make sense out of it, and present it so that people were interested enough and informed enough, meaning that I was hopefully coherent enough that they'd get enough out of it to come back, right? So that is the reason I'm doing it. Yes, I have to admit, I'm on a crusade for science. It's under attack.